All right, so today we're diving into a really fundamental split that's happening in the world of AI. Think about it. We're seeing a massive shift from AI that can just describe the world, write a poem or paint a picture, to an AI that can actually help us build it. We are moving from description to control. And that, my friends, changes literally everything, especially for industries that have to make real, physical things.
And this quote right here just nails it. Industry does not need a librarian. It needs a master engineer. For the longest time, the AI getting all the attention has been this brilliant librarian. It's amazing at finding patterns, writing text, making images. But if you're actually building stuff, you don't need a librarian. You need an engineer, a master engineer, an AI that gets the laws of physics, the rules that actually run our reality.
And this comparison really shows you how deep the differences go. On the one hand, you've got generative AI, the librarian. It works by finding statistical correlations in data. And its biggest problem? Hallucination. It just makes stuff up that isn't real. But then you have operational AI, the master engineer. Its whole world is built on the conservation laws of physics. So when it fails, it's not some random flight of fancy. Its failure is predictable. It's bounded by the laws of energy. These are two totally different ways of thinking about what AI is even for.
So let's talk about this divide, because it creates huge problems out in the real world. I mean, what happens when you ask that brilliant librarian to do an engineer's job? Well, things go very wrong, and they tend to go wrong in really, really expensive ways.
Yeah, this is what the source material calls the capital furnace. It's a perfect name for it. It's what happens when a company sinks millions into creating a digital twin of their jet engine or their factory, but they use the wrong kind of AI. The simulation starts to hallucinate. It comes up with a result that is physically impossible, something that violates the basic laws of physics. The whole thing becomes useless, and all that money, it just got burned up with absolutely nothing to show for it.
So, what is actually going on here? Why can't a standard neural network, which is so incredibly good at so many other things, why can't it simulate even a simple physical system correctly over time? The answer is actually pretty simple, and it's kind of wild.
They drift. That's it. At every single step in a simulation, a standard AI makes a tiny, tiny little rounding error. By itself, it's nothing. But you run that simulation for thousands, maybe millions of steps, and all those tiny errors start adding up. The simulation literally begins to drift away from reality. The model might start to spontaneously create energy out of nowhere or make it vanish. Things our universe just doesn't do.
Now take a look at this number. This is the typical energy drift you'd see from a standard AI model after only 1,000 time steps. I know, that number looks incredibly small, right? But if you're simulating a jet engine or a complex chemical reaction, an error of that size is a total disaster. It means your model's no longer connected to the real world. It's useless.
But now, look at this. This is the alternative. This is the energy drift for a different kind of AI, the HSMN, or Hamiltonian State Machine Network. The drift is hundreds of times smaller. It is so ridiculously small that the simulation stays perfectly locked to the laws of physics. It gives you stable, reliable, and most importantly, correct predictions. This isn't just a little bit better, it's a whole different kind of machine.
So how is that even possible? How do you get that kind of stability? Well, this gets us to the core of the solution. You have to build an AI that isn't physics blind. You have to build it from the ground up with a physics engine right at its heart.
And the secret sauce comes from something called Hamiltonian mechanics. So instead of having the AI just guess what happens next, this approach teaches the AI the system's total energy equation. That's the Hamiltonian. And then it uses a special kind of solver called a symplectic integrator to move the simulation forward in a way that is mathematically guaranteed to conserve energy. No more drift.
And what you get is something the source calls physical certainty. This is so key. The simulation isn't just encouraged to obey the laws of physics, it is mathematically forced to. It literally cannot wander off into some physically impossible state. And that right there is the absolute minimum requirement if you're going to trust an AI with a real-world physical system.
And it's not just about energy over time. It's also about how you handle space. Standard AIs really struggle to represent 3D rotations, which can lead to this bizarre failure mode called gimbal lock. It's basically where the AI loses a degree of freedom and gets stuck. For a robot, that's a complete disaster. The HSMN, on the other hand, uses a more advanced system called geometric algebra, which handles complex rotations flawlessly. No singularities, no getting stuck.
Okay, so you've built this new kind of physics engine for AI. You need to test it, right? You need to push it to its absolute limit. And that brings us to the ultimate test case, the electrohydrodynamic thruster, or EHD thruster. This thing is the perfect end-to-end demo because it tests everything at once: the simulator, the design tools, and the operational AI itself.
And this isn't just some lab exercise. It's a crucible. It's an incredibly difficult challenge that involves multiple, complex physical forces all interacting with each other at the exact same time. And in this world, a hallucination isn't just a weird picture. It's a prediction of a catastrophic failure, like an electrical arc that completely destroys the device. The stakes are real.
So, the AI has to model all of this at once: electrostatics, fluid dynamics, even plasma physics. But here's the really tricky part. It also has to handle both conservative forces, where energy stays in the system, and dissipative forces, like heat loss, where energy is supposed to leave the system. This is exactly the kind of messy, complex, real-world problem that a standard AI just falls apart on.
When you can pass a test that hard, you unlock the true potential of operational AI. This is the moment the AI graduates. It stops being just a tool that predicts the future and becomes a tool that can help us generate a better one.
And this is the real game changer: generative engineering. You see, because the AI understands the fundamental math of the simulation from start to finish, it understands cause and effect so deeply that you can essentially run the physics backwards. This lets you do something called inverse design. You stop asking, hey, what will this design do? And you start asking, to get the result I want, what's the design I need to build?
And the process is just brilliant. An engineer just defines a goal, something simple like maximize the thrust. The AI takes that goal, and because it understands the physics, it works backward through all the equations and it spits out the optimal physical design to achieve that goal. We're talking about turning weeks, maybe months of manual trial and error into just minutes of computation.
So let's just pull it all together. This table really lays out the two different worlds of AI. You've got the brilliant librarian for description and the master engineer for control. It's built on physics, not just stats. It uses a unique, stable architecture, sometimes called a time crystal. And get this, it runs on commodity CPUs, not just expensive GPUs. And its ultimate test isn't generating a pretty picture. It's controlling a real-world physical system, like that EHD thruster.
So here's the thought I want to leave you with. We're really moving past the era of AI as just a clever parrot. We are entering an age where AI can be a true partner in engineering, an AI that understands the fundamental rulebook of our universe. So the only real question left is, what are we going to ask it to build first?